Hello. In this session, we'll go with the very important points of 60A group elements. Before going to exam, it will be easy if you just look at this for 5 to 10 minutes. Oxygen, sulfur, selenium, tellurium, polonium are the elements. Polonium is radioactive element. Half-life is 13.8 days. Oxygen, sulfur, selenium, tellurium are called chalcogens. Chalcogens means ore forming, mineral forming. Electron affinity of sulfur is greater than oxygen. To be precise, oxygen is at the last in this group. Sulfur, selenium, tellurium, polonium, oxygen. Oxygen at the bottom in this group. Electron affinity. Oxidation states +2, +4, +6 and -2. Oxygen can show -2, -1, -1 in peroxides, -1/2, -1/2 in superoxides, 0, +1 in O2F2, +2 in OF2. +4 stability down the group increases, +6 and -2 stability down the group decreases. You can consider this because of the s orbital electrons. Oxygen, sulfur are non-metals. Selenium, tellurium are metalloids. Polonium is a metal. Atomicity, oxygen is a diatomic gas. Sulfur, selenium, tellurium are solids, 8-member solids, octatomic, puckered ring structure. Catenation ability, sulfur, selenium, oxygen, then tellurium. Allotropy, oxygen's allotropic form is ozone. Sulfur, alpha rhombic, beta monoclinic, plastic sulfur, angel sulfur, gamma sulfur, etc. Sulfur 8, S8 will be like crown shape, S6 will be chair shape. S2 is also possible around 1000 Kelvin. S2 will be paramagnetic like oxygen. S2 paramagnetic like oxygen. Alpha beta forms transition temperature is 95.5 degrees Celsius, 369 kelvins. Above 369 Kelvin, beta monoclinic is stable. Below that temperature, alpha orthorhombic is more stable. Remember this point, this is one important one. Compounds, if you look at hydrates, the general formula is H2M or H2E, you can say. sp3 hybridization type, 2 lone pairs, V shape. I mentioned sp3 hybridization type because water you can say sp3 hybridization. In the remaining, pure orbitals participate. That's why the bond angles are very close to 90 degrees. Boiling points and melting points, water is highest because of intermolecular hydrogen bonding. Then down the group increases. So H2TE, H2SE, H2S. Thermal stability, water, H2S, H2SE, H2TE. Down the group decreases expected. As bond length increases, bond energy decreases, thermal stability decreases. Dipole moments and bond angles also same. H2O 104.5 degrees, H2S 92, H2SE 91, H2TE 90 degrees. Because of the pure orbitals participation, these are very close to 90. Water sp3 hybridization, 2 lone pairs, it is 104.5 degrees. Reducing nature, H2S less than H2SE, H2TE because of the decrease in bond energy. Water is not a reducing agent. Remember this point. Water is not a reducing agent. Then look at the halides. Oxygen can form OF2 type. Okay, now oxygen fluoride it is, oxygen difluoride. O2F2 is also possible. Cl2O, chlorine, oxygen, Cl2O, ClO2, Cl2O6, Cl2O7. We will discuss about this in group 7. OF2 bond angle is 103 degrees. Cl2O bond angle is, Cl2O bond angle is 111 degrees. You can notice here, Cl2O, 2 chlorine atoms are very big. Because of this, the bond pair repulsions will be a very interesting thing, and it is more than 109 degrees 28 minutes. In case of OF2, it is less than 109, 103 degrees. But in case of Cl2O, it is more than 109, that is 111 degrees. OF2, there is no hydrolysis, but Cl2O, it undergoes hydrolysis to form HOX or you say HOCl type. Remaining hexahalides MX6 type or you say EX6 type, sp3d2 hybridization, octahedral. The most important one is SF6. SF6 is most important compound. Tetrahalides MX4, sp3d type, CISA, one lone pair will be there. Best example is SF4. These are Lewis acids and Lewis bases because of the presence of vacant orbitals, Lewis acids because of the presence of a lone pair Lewis bases. Dihalides like MX2 type, sp3 hybridization, two lone pairs will be there, V shape, SCl2 example. Monohalides M2X2 type, sp3 hybridization, S2Cl2, it is open book shape. S2Cl2 is open book shape. S2Cl2 is very much important reaction. Its important reaction is mustard gas formation. S2Cl2 when reacts with ethylene, it forms mustard gas. That's one very important one. Coming to some oxides of this, oxygen oxide, you can say OO2, that is O3. We will discuss about O3 in a separate section. Acidic character, normally if you see SO2, SeO2, TeO2, these are dioxides. Sulfur dioxide is more acidic. Down the group the acidic character decreases, and trioxides also same case, SO3, SeO3, TeO3, acidic character decreases. For dioxides as well as trioxides, acidic character and stability both decreases down the group. For the same atom, if you see, higher the oxidation state, higher is the acidic nature and higher is the stability. SO3 greater than SO2 greater than SO. SO generally not formed. SO2, the preparation is very simple, S plus O2 SO2. Otherwise, any sulfide ore combustion will be giving you SO2. Otherwise, sulfite SO3 minus 2 when treated with acids, it forms again SO2. SO2 is anhydride of H2SO3. SO2 is a colorless gas. SO2 is a bleaching agent in moist, and it is a bleaching agent due to reduction. It is a temporary bleaching agent. These are very important points. SO2 intermediate oxidation state plus 4. Because of this, it is a reductant as well as oxidizing agent. It is having a lone pair, so Lewis base. sp2 hybridization bent 119 degrees. One p pi bond and one d pi bond is there. You can see the structure. SO2 reduces potassium permanganate KMnO4 to Mn plus 2. It reduces Fe plus 3 to Fe plus 2. You can remember these reactions. And one very special reaction of SO2 is when this is treated with sodium hydroxide, it forms sodium sulfite, Na2SO3. But if you are using SO2 excess, that sodium sulfite will turn into sodium bisulfite, NaHSO3. It is very similar to carbon dioxide sodium hydroxide reaction, Na2CO3, NaHCO3. Otherwise, calcium hydroxide and carbon dioxide reaction. Very similar to that. It is not mentioned here, but you can remember this SO2 reaction. Very, very special. SO3 is prepared by SO2 and O2 in the presence of V2O5 or PT or NO. These are the catalysts. SO3 is formed. This reaction. Generally, in the preparation of H2SO4 by contact process, we use this reaction. This is exothermic reaction. As this is exothermic reaction, the temperature should not be very high, but at low temperatures the reactions will be slow, so we maintain optimum temperatures approximately 700 kelvins, and here number of moles are decreasing, that means volumes are decreasing, so pressure should be high, so 2 atmosphere pressure like that we use. SO3 is acidic in nature. It is anhydride of H2SO4. When this is added with water, it forms H2SO4. So anhydride of H2SO4. It is only oxidizing agent because it is in the highest oxidation state plus 6. So only oxidizing agent. sp2 hybridization, planar, no lone pairs are there. 120 degrees angle, the distance is 1.42 angstrom. Of the 3 pi bonds, one is p pi, remaining are d pi. D orbitals of S sulfur and p orbitals of oxygen. You can see here. I just give a moment gap here. You just see the structures and all. SO2 and SO3. Coming to oxy acids of sulfur. Sulfur oxy acids here mentioned around 1, 2, 3, 4, 5, 6, 7, 8, 9 are mentioned. We'll go one by one. Sulfurous acid, H2SO3. One point about the sulfur oxo acids. All are sp3 hybridized. All are dibasic acids. All are dibasic acids. All are sp3 hybridized. So the major structure will be tetrahedral only, electronic structure. If any lone pair is there, that will turn into pyramidal. Okay. So first one, sulfurous acid, H2SO3 plus 4 oxidation stage. As one lone pair is there, it is. As one lone pair is there, it is pyramidal in shape. And you can see another structure of this in which it is having a sulfur hydrogen bond. Because of this, it is a reducing agent also. It's a reductant. one very special point. Thiosulfurous acid. Thiosulfurous acid is H2S2O2. Above structure only you see. In the above structure, double bond oxygen is there. Na? In the double bond oxygen place, double bond sulfur. So the sulfur which is terminal, that is -2 oxidation state. The central sulfur is +4 oxidation state. The average will be +1. Thiosulfurous acid. These two acids you can consider as sulfurous acid series. Then sulfuric acid, H2SO4 +6 oxidation state. Very good oxidizing agent because of the highest oxidation state. Very good dehydrating agent. Alcohols can be converted to alkenes. You can notice formic acid, HCOOH, is converted to carbon monoxide. Oxalic acid is converted to carbon monoxide and carbon dioxide. Sulfuric acid, dehydration reactions. Sucrose, if you take, that will be converted to carbon. It's a very good oxidizing agent. It oxidizes sulfur to sulfur dioxide, carbon to carbon dioxide. A very good oxidizing agent. And it's a pickling agent. Its structure is S double bond O, two OH groups are there. And it is less volatile. So more volatile gases like HCl, HF and HNO3 acids can be prepared from their salts by using this one. And H2SO4 is a dibasic acid, so it forms two series of salts, sulfates and bisulfates, SO4 -2 and HSO4 minus. The Ka value, Ka1, loss of first proton will be very high, more than 10, and Ka2 value is less, 10 to the power of -2 approximately. So loss of first proton will be easy in case of sulfuric acid. So sulfuric acid is prepared by contact process. Sulfuric acid gives prepared by S gives rise to SO2, SO2 to SO3, SO3 plus sulfuric acid gives you H2S2O7 oleum. That oleum, when added with water, it turns into H2SO4. We will discuss about this in a detailed session later. Now in the same, one oxygen is, if it is replaced by one sulfur, it is called thiosulfuric acid. Formula you can see here, H2S2O3. In H2S2O3, one central sulfur is with +6 oxidation state as sulfuric acid, and one sulfur which is replacing oxygen with -2 oxidation state. The average oxidation state will be +2. Dithionous acid formula is H2S2O4. Dithionic acid, H2S2O6. This dithionous and dithionic acids will be having sulfur-sulfur bond. When they are having sulfur-sulfur bond, they are called thioacids. Dithionous acid, dithionic acid. Sulfur-sulfur bond will be there. You can remember the structure very easily. Remember one point, in all these, they are dibasic acids. So 2 OH groups you need to give, and sulfur must contain either 6 bonds or 4 bonds. Use this simple logic, you will be getting. Dithionous acid, each sulfur will be having a lone pair. You try these structures. And dithionic acid, each sulfur will be having 2 double bond O oxygens, 1 OH group, and 1 sulfur-sulfur bond. The oxidation states also you can see, dithionous acid is +3, dithionic acid is +5. Polyethylenic acid also you can take here along with dithionic acid, H2S2 plus NO6. Between two sulfurs you can keep more 6 sulfurs. Okay, now 3, 4, 5, 6, all these sulfurs you can keep in between 2 sulfur atoms. That is called polyethylic acid. In polyethylic acid, whatever the sulfurs coming in between 2 sulfurs, they will be having 0 oxidation state. Oleum pyrosulfuric acid, H2S2O7, it is having SOS linkage. 2 sulfuric acids you keep together, remove one water molecule. Okay, now SOS linkage will be there. That is pyrosulfuric acid. Marshall's acid is H2S2OH. Marshall's acid will be having SOS linkage, SOOS. Like oleum only, pyrosulfuric acid SOS linkage, in this SOOS. Remember, in every structure there is a double bond O to sulfur, and there is mandatorily one OH group on sulfur, minimum one OH group on each sulfur. Carros acid is H2SO5. Marshall's acid is called peroxodisulfuric acid. Carros acid is called peroxomonosulfuric acid. Oxidation state is +6 only. Okay, now it won't come more than +6 because sulfur group number is 6. +6 oxidation state is the maximum you can say. So these are the important points of sulfur. We will see a few more. See here, ozone. Ozone can be prepared by sending oxygen through silent electric discharge. 3O2 gives rise to 2O3. Delta H is equal to plus 272 kilojoules. You can see here. That means it is an endothermic reaction. That's why silent electric discharge. And remember, you cannot convert all the oxygen into ozone. Only 10% will be oxygen. 10% will be converted. Okay, now based on this, some questions will also come. Properties: ozone is diamagnetic oxidizing agent. Ozone is a pale blue color gas, and when it turns into liquid, it is thick blue color, and when it turns into solid, it is violet black solid. When ozone reacts with mercury, it forms Hg2O. Mercury flowing nature, mercury moving nature is arrested or is stopped by ozone. This is called a tailing of mercury. Tailing of mercury. And Hg loses here meniscus, that is one very important one. And ozone preparation technique is called Siemens or Brody's ozonizer techniques. Sulfur dioxide when treated with oxygen, ozone, it forms SO3. SnCl2 when treated with ozone, it forms SnCl4. In these two reactions, oxygen is not released. Otherwise, in all the oxidation reactions of ozone, O2 is going to be an important byproduct. But in these two reactions, ozone is completely utilized, O2 is not coming. Remaining all you can easily remember. For example, lead sulfide converted to lead sulfate, O2 comes out. Reducing agent, okay, now ozone can function like reducing agent also. H2O2 plus ozone, H2O, BaO2 plus ozone, BaO. So number of oxygens at what hydrogen peroxide and barium peroxide are decreased, so you can consider this as reducing agent. Ozone is very important in identifying the position of the multiple bonds, double bonds and triple bonds in ozonolysis reaction of alkenes and alkynes. Ozone structure will be like this. Ozone, very important question they ask you from chemical bonding is the formal charges. The central oxygen formal charge will be +1. One oxygen with single bond will be -1. One oxygen with double bond will be 0. The formal charges is very important question of ozone. And the structure is sp2, one lone pair. Test for ozone is it turns moist starch iodide into blue, and tetramethyl base paper violet. Ozone. Hypo. Hypo is another one. Na2S2O3 5H2O, sodium thiosulfate 5H2O. This hypo is not much discussed now in NCERT, but you can have a look. Na2SO3 plus SNA2S2O3 preparation. Na2S plus Na2SO3 plus I2 also will give you Na2S2O3. The very, very important reactions are when it treated with silver nitrate, it forms Ag2S2O3, then it turns into Ag2S, which is a black precipitate. With silver halides like AgCl, it forms a complex Na3AgS2O3 taken twice, sodium argentothiosulfate. With chlorine and bromine, it forms Na2SO4 and sulfur. With iodine, it forms Na2S4O6, which we call sodium tetrathionate. This reaction generally they ask you for the oxidation states. Na2S2O3 oxidation state and Na2S4O6 oxidation states generally they ask you. So sodium Na2S2O3 is sodium thiosulfate, Na2S4O6 is sodium tetrathionate. The structure you can see, it is nothing but Na2S2O3 is nothing but H2S2O3. H2S2O3 is nothing but thiosulfuric acid. Two negative charges oxygens. In those two negative charges, you can keep sodium plus also along with them. So this is used in fixing agent as photography processes as anti-chlor. Anti-chlor means to remove chlorine because it can react with chlorine. In the estimation of iodine also it can be used. This is about sixth group, very important points. We will meet with other group in next session. Thank you.